Starting 5.5 combination reactions and 5.6 replacement reactions. Okay, remember combination reactions we had as A plus B goes to AB. Now this can be elements or this can be compounds that do this, that go from one thing to another. So let's break it down a little bit and take some examples. For instance, if I take magnesium and I add to it oxygen and I light it on fire, then I'm going to get magnesium oxide. Now we still have to go through and balance, which would be doing this, but this is a combination reaction, a simple one. If I want to go a little bit more advanced, then I could take a formula that's from acid rain, and what happens is sulfur trioxide is a pollutant in the air and a gas, and when it mixes with water it actually makes sulfuric acid. This is a combination reaction. So both of these are combination reactions. So the general form is I have two things and it makes one. So opposite of a decomposition. Okay, on replacement reactions we have two different kinds. We have single and double. Remember, single can have A plus B plus C giving Cb plus A. So I can replace the positive ion, or it can be AB plus D giving AD plus B. Or I can replace the negative ion. So in a regular reaction, we could look at, say, K plus H2O yields, well, you got to know on this one, and we haven't covered this yet, that water will split up into the groups H and OH. So OH as a hydroxide sticks together. So we're going to replace the positives here because K and H are both positive, and we'll go get KOH with hydrogen getting kicked out by itself. And remember, hydrogen is an H2. So as we do that, we now need to balance the equation. And if we went through and balanced the equation, we'd end up with 2 in front of the potassium, a 2 here, and a 2 here. Okay, and you could take the time to do that. So that is a single replacement reaction. On a double replacement reaction, remember we have AB plus CD yields AD plus CB. Positive is always written first. So let's take a look at a reaction that would be a double displacement or double replacement. That would be like barium chloride reacting with sodium carbonate to yield what? Now, if you are familiar with the math term FOIL, FOIL, first, outside, inside, last. We do a form of that, but we call it OI, outside, inside. So we're going to take and put the outsides together, and remember CO3 is a group, and we're going to take and put the insides together. And I always started with my positive ion, so I know it goes first. Now, just like we did with the redox, we want to know what the charge of each of the elements is, or groups are that are going to stay together. So here, barium is in the second column. It's going to be a +2. Each chlorine is a -1. I don't want to know how many. That was to balance the compound itself. Sodium's in the first column. It's +1. And carbonate as a group has a -2 charge. So now I'm going to take them over here. I'm going to do my outsides first. So I'm going to put barium with carbonate. And barium has a +2 charge and carbonate has a -2 charge, so they balance out. And I'm going to have sodium, which is a +1 charge, going with chlorine, which is a -1 charge, and they'll balance each other out. Now again, all this stuff I either erase or I do on scratch paper so that my final reaction is not messed up. Now you'll notice here it's not balanced. I've got one barium on the left, one barium on the right, 2 chlorines on the left, and 1 chlorine on the right. So I need to put a 2 in front of here. When I do that, the rest of the equation balances out. So it takes a little bit of time with double displacement, but just remember OI. Remember FOIL from math, and we just take the OI, outside, inside. Okay? Okay, I've given you a couple of word problems here. Go ahead and stop the video, write them down, see if you can do them by yourself. I'll give you a few seconds here, and then I'm going to start it up again and show you how to do it. But try and do it on your own. Okay, I'm coming back to show you. Sodium iodide, sodium is Na, and Na has a +1 charge. Iodide is capital I, and it has a -1 charge, so I just need one of each. Reacts with means plus. Chlorine gas, chlorine is Cl, it's one of our Braunhilfe or our diatomics, so we need 2 of them. And we're going to react that. Now, chlorine wants to take a -1, so it's a minus, and iodine's a minus, so we're going to switch those 2 places. So sodium is going to go with chlorine. So I got two girls fighting over a guy, and iodine's getting kicked out. Iodine is also a part of our Braunhilfe, so we'll need 2 of them. Now to balance it, we've got 2 iodines, so I'm going to put 2 iodines, and that gives 2 chlorines, and now we're balanced. So that's a single replacement. Now this would have been aqueous, AQ, a cute little thing here. This would be in a gas. Sodium chloride would have been aqueous or in solution, and iodine would be aqueous. Alright, so let's go on to the next one, the double displacement. See how you did on that one. Sodium chloride we already wrote up there as NaCl. That's a pretty easy one to remember. In order to get this to react, of course it's going to be aqueous or in solution. Plus silver nitrate. Silver is Ag, has a +1 charge. Nitrate is one of our polyatomics, it's NO3. And it also has a -1 charge, so +1, -1, already balanced. And it would need to be aqueous in order for it to react. Now we're going to do OI, outside, inside. So OI, outside. Sodium is going to go with the nitrate group, so I'm going to go NaNO3. Na is +1, NO3 is -1, so already balanced, and it would be aqueous. And then I'm going to go the I, insides. So silver, which is a +1, is going to go with chlorine, which is a -1. And this actually is a precipitate or a solid. It'll fall out of solution. And don't forget, when you get that all done, you're going to go back and you're going to erase your little helps so they're not there. Now, this is already balanced because every ion in this double replacement was a + or -1, so they already balanced themselves. Okay, let's look at this. Classify each of the following reactions as redox or non-redox, then as decomposition, combination, single replacement, or double replacement. You don't have to do a lot of work in order to see if it's a redox reaction. If I have any element that's by itself, it's going to be 0. And if it combines, it's going to be a redox. So this is a redox reaction because the charges will change side to side. It didn't ask me to identify which was oxidized and which was reduced, but we could do that very quickly. Remember, hydrogen, when it combines, is a +1, iodine is a -1. So going this way, hydrogen loses, or gains electrons and becomes more negative. So it's GR, which is reduction, and it's the OA. And then iodine would lose electrons, and it would become LiO, and it would be the Ra. Now remember, that's just shorthand. Excuse me, LiO means oxidized, and Ra means the reducing agent. This is a redox reaction, and it's going from one thing to 2 things, so it's falling apart, so it's decomposition. Okay, I'm going to have you pause the video. I want you to see if you can figure out the others right here, and then I'm going to come back and do the rest with you. Okay, I'm coming back. Now, anytime you have an element by itself on one side and it's in a compound on the other side, you know you've got redox. So again, On B, I can really quickly say, oh, this is a redox reaction because this oxygen's by itself, so it's going to be 0, where here it's a -2 for 2 of them. And here it goes to minus. So this one is a redox. You don't have to know anything else, but see that it changed charge once. So there's got to be another charge in there, even if I can't find it. The next thing I want to look at is see what is happening with the equation. I went from one thing to two things. So because I did that, this is another decomposition. The next one, I've got elements by themselves again, so 0, 0, and then they combine. And that's all I need to know. If they had asked me which was oxidized and which was reduced, then I'd need to know more, but this did not. So just because I know they went from zeros to a charge, then I know it's a redox also. And I've got two things here going to one. So I'm combining it, so this is combination or synthesis if you remember that name. But I think they'll be using combination for this one. Now on the next one, remember our dance scenario, we've got a couple and a single giving a couple and a new single. So this one right here is going to be single replacement. And in single replacement, we also have, I ran out of room, there's your mint. I've also got elements by themselves and then combining. So because I've got elements by themselves and combining, this also is a redox. Now the one on the bottom, we've got a couple, a couple, a couple, and a couple. So we've got a double displacement going on here. I'm going to change to blue so you can sort of see double displacement or replacement. Different books use different things, so sometimes they say replacement, sometimes displacement. Now, on this one, though, the charges of all the elements stay the same all the way through. So this is non-redox. We don't have any elements that have gone to be their element by themselves. And if we look, we've got sodium, which is a +1. PO4 that stays as a group as a -3. We've got Ag is a +1, NO3 is a minus, Ag is a +1, PO4 again as a group is a -3, Na is a +1, NO3 as a group is a -1. So no charges changed. So this is non-redox. Alright, so we're going to do some worksheets in class that have to do with this and sort of play with what is redox, what isn't redox, what identify, how do you identify it. So hopefully that'll help, and this is a little bit shorter lesson tonight. Last time was a little bit longer, so hope you enjoyed it. See you in class.